Thanks very much. Apologies for that fiddling around. So thanks, Abby, for the introduction and the invitation, and good evening, everyone. Thanks very much for giving up an hour of your time to hear the story that I've got to tell tonight. So if you're expecting to come along to a talk on deep geological disposal of UK nuclear waste, then you've come to the right place. So just a little bit about me. I'm a geologist. I spent most of my career in oil and gas exploration and production, both working at the University in Birmingham opposite King Edward School, and also working for big exploration companies like British Gas and Shell. And then 6 years ago, I thought I wanted to do something new and fresh and interesting with my skills. So I found myself in my present position, which, as Abby said, is Chief Geologist for Nuclear Waste Services, and that's what I'm going to talk to you about tonight. So what I really want to do is make certain that I think we've got an hour slot, something like that, but I want to make certain that there's time for questions after, because my experience of giving these talks is people have got a huge variety of different questions, some of them on the science and geology side, and some of them on the people side and policy and funding and that sort of thing. So let's get started. Going to cover a whole range of different topics, starting with some basic physical chemistry and then moving on to the sort of rocks in which we might dispose of this material. The photograph that you see there is looking up the shaft of an underground rock laboratory in France. It's constructed at the same place where they plan to build their geological disposal facility. And in all my slides, you'll see in the left-hand corner, there's a little icon saying GDF, and that stands for Geological Disposal Facility. So the UK is not alone. There are other countries that have been accumulating nuclear waste for many tens of years, which are now facing the challenge of how to dispose of it. Good. Well, I realize in principle, we've got a whole range of different age groups online here, I think from years 7 to years 13. So I thought I would just start with some basic physical chemistry so that everyone understands what I mean by radioactivity and radioactive waste. And the point about radioactivity, it's a property of some materials, particularly when you get down to the lower end of the periodic table, particularly row 7, the actinides, where some materials, basically they have too many neutrons in the nucleus, in the central part of the atom. And nature solves this problem by getting rid of those neutrons, either in the form, as you can see there on the slide, of electrons, fast electrons, in the form of what's labeled there as alpha radiation, which is basically the nucleus of a helium atom, 2 protons, 2 neutrons, and also emitting what's called gamma radiation, which is a type of electromagnetic energy. So radioactivity, in the way in which I'm using it, refers to ionizing radiation. And I'm sure people are aware that ionizing radiation potentially can harm people, it can harm animals, it can harm DNA because it's got so much energy. And that's why we need to be very careful in the way in which we dispose of radioactive waste. Well, one of the properties of radioactive materials, and I'm sure a lot of people online will be aware of this, is that unlike, for example, toxic chemical waste, which will be as harmful in 10,000 years as it is today, the point about radioactivity, because of the way in which radioactive elements get rid of their neutrons, it means that those elements change over time and become less radioactive. And the rate at which they become less radioactive is often described in terms of what's called a half-life. And the half-life is the amount of time for the level of radioactivity to decay to a half of its starting point. So why do I show a big bar of chocolate in the bottom right there? Well, a friend of mine who used to teach at the University of Leeds, he decided it would be a really neat idea to explain half-lives in terms of splitting up a bar of chocolate. So for the students that were sitting on the front row, he gave the student on the left-hand end a bar of chocolate, asked him or her to break it in half, pass it on to the next person. They had to break it in half, pass it on to the next person. And of course, by the time that bar of chocolate has gone through 10 people, for example, 10 half-lives, 10 to the power of 2, sorry, 2 to the power of 10, then it's less than 1,000th of its original size. So this is really important in that the hazard associated with radioactive materials reduces over time. Okay, still staying on the theme of just understanding radioactivity and half-life. So the graph in the top left there, the different colored lines that you can see represent the rate at which different parts of the UK radioactive waste inventory decays over time. So the level of activity, the level of radioactivity is shown on the vertical axis on the left, and time increases from left to right on the horizontal axis. And you can see that it's a logarithmic scale. Now, there's far too much detail in there, but the really important point that I want you to take away is that after about 100,000 years, the overall amount of radioactivity emitted by all the different types of waste that make up the UK radioactive waste inventory, over 100,000 years, it reduces to the radioactivity of natural uranium ore. In other words, the original rock from which the radioactive uranium was mined and then processed such that it can be used as fuel in power stations and other applications. So 100,000 years, and that's a long time, isn't it? And I'm going to talk about the significance of that very long period over which we need to protect people and animals and the environment and the way that we go about that. The image in the bottom right there is of a mine in South Australia, very remote part of South Australia in the desert called Olympic Dams. And this is the largest uranium mine in the world. So it's really just pressing home the point about the fact that uranium, of course, is mined. It comes from somewhere. It comes from uranium oxide that occurs naturally in rocks. The image, that space image that you can see there, the colors are false, but it shows the sort of scale of activity associated with mining uranium that's then exported around the world for use in power stations and other applications. So how much waste has the UK got to dispose of? The answer to that, and it's a fairly meaningless figure, it's about 750,000 cubic meters of waste. Now, to give you an idea of what 750,000 cubic meters looks like, if you've been to London and you've seen Big Ben just beside the Houses of Parliament, imagine a cube, imagine a box, the height of Big Ben. That box, if it was cubic in shape, would have a volume of about 750,000 cubic meters. In terms of international mining facts and figures, that's not really very large. There are many mines around the world which mine that amount of rock over a period of a year or less. Of course, the important thing about this 750,000 cubic meters that I'm talking about this evening is that it's potentially very hazardous, and we need to be very careful how we dispose of it. So that's the volume. What about the origin of the UK's nuclear waste? Well, most of it, about 95% of it in terms of volume, is a byproduct of nuclear power generation. So the photos that you can see there in the top left is an artist impression, a sort of computer-generated graphic of two new nuclear power reactors that are being built on the North Somerset coast, about 130 kilometers from Birmingham. You might have seen it in the news. It's called Hinkley Point C. Like I say, on the coast of North Somerset, at a cost of about £25 billion. It's being built by a French company, and that's the first of probably a new generation of nuclear power stations that the UK is going to build over the next 20 or 30 years. The photo in the bottom right there just gives you an impression of the scale of construction of modern nuclear reactors. So that's a picture from that Hinkley C power station in North Somerset. And what you can see there is a crane lifting what's called the reactor pressure vessel from the construction site into its final resting place as part of the reactor assembly. The crane is often called Big Carl, and it's the largest and heaviest land crane in the world. And if you ever go down to the Hinkley C is near Bridgewater in North Somerset, and you can see the number of cranes there. You can get an impression from that photo of the scale of the building operation that's required to build these sort of very, very carefully specified modern nuclear reactors. So about 95% of the waste by volume for the UK comes from nuclear power generation. You will be aware that a tiny but significant volume of nuclear materials are used by the medical industry for medical imaging, and also for things like radiotherapy for curing cancer. That's a tiny, less than 1% of the total inventory. And then thirdly, let's not forget, like France, the UK within Europe, along with France, has a nuclear defense capability. So a small but significant portion of the waste that we're needing to dispose of comes from the defense program. And you might ask, where is the material stored today? Well, hopefully that map is not too small there. And the answer is it's stored at about 25 different surface storage sites around the country. Most of them within England, a few within Scotland, including way up on the north coast there, and a few within Wales. And that material will remain stored there until my company, that is Nuclear Waste Services, is able to construct a geological disposal facility, at which point we will begin the process of moving radioactive waste presently stored above ground to wherever that geological disposal facility is located, and beginning to put it underground and dispose of it permanently. So about 25 sites around the country where nuclear waste is presently stored. More than 80% of it is at a huge industrial complex in northwest England, just to the west of the Lake District National Park that you might have heard of, and it's called Sellafield. And Sellafield has been in existence really since the very start of when the UK got into nuclear technology and into the nuclear industry, which was really immediately after the Second World War, actually in 1946, not even the 1950s, but actually back into the 1940s. So the photo in the top left there shows Sellafield. The two tall chimneys, they're not actually chimneys that you can see there. One of those has already been taken down and the other is halfway to being dismantled. Those are stacks for generating plutonium for the defense program. The chimneys that you can see on the right with a puff of steam coming out of them, that's an experimental power station that was built in the 1950s. And then the spherical structure that you can see in the foreground is one of the early experimental advanced gas-cooled reactors. So at Sellafield, a lot of the waste is stored and is cooling in ponds. So in the bottom there, you can see a pond that's beneath a roof, and you can just see through the sort of beautiful crystal clear water of the pond, you can see flasks that contain heat generating waste that's cooling down over a period of several decades. Some of the older waste management solutions are shown in the top right there, and this is ponds which are open to the atmosphere, so they're accumulating all sorts of stuff, wind-blown dust, bird droppings, which is getting into the water there and mixing with the nuclear waste. And really this sort of summarizes why there's an urgent need to find a location for a geological disposal facility and begin to dismantle Sellafield and put the nuclear waste that's stored there underground. Because it's extremely secure where it is. It can be stored there, for many years, tens of years, hundreds of years. But in order to maintain the security and the very, very high standards of storage that's required, it's extremely expensive. It's about £3 billion a year that it costs the taxpayer. And that £3 billion a year lasts in perpetuity until we, nuclear waste services, are able to construct a geological disposal facility in which we can permanently dispose of this nuclear waste material. So some of the less hazardous waste, we call it intermediate level waste, and the point is that it's non-heat generating, has already been packaged. So the photo on the left there is from Sellafield that I showed you in the last slide, and this shows 500 litre stainless steel drums that contain relatively low level, intermediate level, non-heat generating nuclear waste. And those drums are stored at Sellafield, ready to go underground into a geological disposal facility. The cutaway on the right just gives you a feel for what's inside the drums. The material, the nuclear material, is not just sort of pushed in there and rattling around. It's actually mixed in with it's cement really, a sort of very high pH, very highly alkaline cement. And you can see dark pieces of intermediate level waste, mainly shavings from the metal material in which some of the fuel rods are jacketed. But the intermediate level waste here within those 500 litre drums is floating within it's sort of dispersed within this highly alkaline cementitious grout. And the reason for the high pH, the reason for the high alkaline, is because radionuclides, so radioactive materials, are much less mobile in a high pH chemical environment. So let's go on to say a little bit about GDFs. And you remember the acronym GDF, I just use it I just use it for shorthand to describe a geological disposal facility. So this is a cartoon, if you like, of what a GDF could look like. So the surface facilities, they will definitely be on the land, and that's significant because I'll talk about it in a minute, but the subsurface facilities, the underground facilities, could be under the sea, but we'll say a few words about that later. But the cartoon shown here shows the surface facilities immediately above the galleries and tunnels and vaults where the nuclear waste is actually disposed of. So the surface facilities, between 1 and 2 square kilometers, and they'd look like a sort of fairly low level industrial complex, almost certainly with a railhead coming into them. In other words, some of the nuclear waste will be, or most of the nuclear waste will probably be brought in by train. The areas underground in which the nuclear waste is actually disposed of, you can see them divided into 2 halves: low heat generating waste areas and high heat generating waste areas. And they'll be at least 200 meters below the land surface. And the reason for that 200 meter figure I'll talk about right at the end of this presentation. They might be accessed by a couple of vertical shafts, essentially a lift, a bit like that photo that I showed from France in my opening title slide. Or what you can see here is there's a sort of spiral roadway called a drift or an adit, in which a train or remotely controlled trucks or whatever could make their way from the surface down to the disposal areas. And then the disposal areas themselves, and as I said, clearly divided into two halves: low heat generating waste disposal areas and high heat generating waste disposal areas. Now, about 85% of the total volume of UK nuclear waste comprises low heat generating material, that intermediate level material that I showed um, packaged within those 500-litre stainless steel drums in the last slide. But that's curious, isn't it? Because actually you can see the high heat generating waste disposal area here actually takes up a greater area. And the reason for that is because the material on the right is generating heat, it needs to be spaced more widely in order for the rock to be able to wick away the heat. What we can't have is the material disposed of in such close proximity to one another, tightly packed in, that it generates so much heat that that actually compromises the engineered barriers that are designed to keep the whole facility safe. So only about 15% of the total volume of the inventory is that heat generating waste. But as you can see there, it occupies more than half of the footprint of a GDF. So low heat on the left, high heat on the right. So let's just say a little bit about the kinds of geology, the kinds of rocks that could be suitable for a geological disposal facility to be built in. And Britain's a fairly small island compared to many other countries, but despite that, we've got a huge range of different sorts of geology, different sorts of rock type, different ages of rock type. We've got just about everything on this little island of ours. But in spite of that, we divide all that rich diversity of different rock types into three main categories of rock in which a GDF could be constructed. And I'm going to go through those three categories one after the other now. The first of them is claystone or mudstone. In other words, very fine-grained, compacted and compressed sedimentary rock. And the point about claystone is that fluids can move only extremely slowly through it. So slowly that the main mechanism for fluids and materials to flow through these sorts of very fine-grained rocks is a process called diffusion. The photos that you can see here are again from the underground rock laboratory in France. It's about 200 kilometers east of Paris, and it's on the site where the French will be constructing their geological disposal facility. It's at about 550 meters depth, and it will be constructed in a Jurassic, so about 180 million years old, Middle Jurassic claystone, very similar to some of the claystones that we're looking at for GDF construction in the UK. So about a ½ kilometer below the land surface, fine-grained claystone. And as I say, the important thing about claystone is that fluids move only very slowly through these sorts of rocks. I should just say a word about what I mean by fluids. I'm mostly talking about water, what we call groundwater, in other words, underground water. But also the reason I use fluids rather than water is because I want to include gas. There are two main ways in which radionuclides, so radioactive materials, could migrate from depth up to the surface. And that's either within water or within gas. And this is why I'm putting so much emphasis on the way in which water and gas move through these rocks, because wherever we construct a GDF, it has to be constructed in rocks in which fluids either move very slowly or are unable to move up to the surface. So fluids in this context means water, but also gas. Okay, so before I move on to the second of the three rock types, just worth saying a few words about a nice sort of analogy that we use for a GDF. So this is what I often call a natural GDF, and it's a uranium mine in Arctic Canada. So you can see there the photo. It's from northern Saskatchewan. The cartoon on the left shows the uranium ore is encased within that yellow rock about 430 meters below the surface. So you've got dark blue uranium ore sitting within a yellow rock. That yellow rock is a claystone. It's a bit older, it's a lot older than the French claystone, for example, but it's got the same sort of properties. Very fine grained, diffusion dominated, fluids move only extremely slowly through it. And the important thing about this uranium mine, and it's called Cigar Lake, is that there's no evidence of radioactive contamination at the surface or in the rocks between where the ore is and the surface. So that's why we refer to it as a natural GDF, because nature has very effectively demonstrated how a fine-grained claystone can seal in that potentially harmful material, in this case for not millions of years, not tens of millions of years, but more than 1 billion years. Okay, back to my previous theme. So I was going through the three main categories of rock in which a GDF could be constructed. Number one is claystone. Number two is rock salt. So same chemical composition as the table salt that you use on your fish and chips, sodium chloride. And you will be aware, I think, that rock salt occurs naturally. We have two sort of geological occurrences of rock salt in the UK, within Permian rocks and within Triassic rocks. And the point about rock salt is because it has a sort of finely interlocking crystalline texture, fluids can't flow through it at all. It has no pore spaces and it has no cracks, so fluids can't flow through it. The photos that you see here are from the world's only operating GDF. It's in the desert in New Mexico that's receiving intermediate level, that's non-heat generating waste from the US defense program. The other point that I've made in the annotation there is it's a really effective, rock salt is a really effective barrier to fluid flow, but also it's self-sealing. Now, what do I mean by that? Well, when you put rock salt under the sorts of forces or stresses, pressures that exist hundreds of meters below the Earth's surface, it actually begins to behave quite plastically, a little bit like putty or plasticine. And what that means is that any cracks or fractures within rock salt seal up, because they'll just sort of flow together. And this is why rock salt has no porosity, and this is why rock salt is a really effective material to act as a barrier to water and gas. And then my third category of rock type in which a GDF could be constructed is a real bucket term that I've called higher strength rocks. So this might be granites or slates or volcanic rocks. The point about high strength rocks is because they're so compacted and brittle, they contain networks of connected fractures. And as soon as you think about open fractures deep underground, hopefully you can see the point I'm trying to make, and that is that water and gas can potentially move quite rapidly through those fractures. They're pathways along which water and gas can potentially move quite quickly. And therefore, the point about higher strength rocks is that if we were beginning to home in on high strength rocks as a potential site for GDF construction, we would need to demonstrate that deep groundwater systems, so deep underground water, was unable to flow up to the surface. So an example would be if that water was highly saline and therefore denser. If it's denser, it's heavier and it's not going to flow up to the surface. But potentially these rocks, fluids can move quite rapidly through them, relatively rapidly, because of the fractures. Having said that, the photos that you see here, as it says, are from Sweden, where they have just this year, SKB, which is our equivalent waste management organization in Sweden, have received a license from the government to begin construction of their GDF to dispose of spent fuel from their power generation program in higher strength rocks, in granite gneisses to be specific, at a place called Forsmark on the Baltic coast. Likewise, Finland have now constructed their GDF, also in high strength rocks, and are ready to begin disposing of materials in less than 2 years' time. So you might remember 4 or 5 slides ago when I just gave you a sort of idea of how a GDF might look. I was very careful to say that in that cartoon I showed you, the waste disposal areas were sitting vertically beneath the surface facilities, but that doesn't need to be the case. And what you see here is a cartoon that shows the waste disposal area, the surface facilities on the coast and the waste disposal areas under the seabed. And the separation distance could be as much as 12 nautical miles or 20 kilometers. The significance of that 20-kilometer figure is that up to 20 kilometers from the coast is all Crown estate land, or basically government land. Therefore, the land ownership issues are very straightforward. And we find that when we're talking to communities that might potentially host a GDF in their area, they might have a GDF built in their area, they're very interested in the idea that the actual tunnels and vaults and galleries in which the nuclear waste material might be disposed of is far offshore beneath the seabed, away from any built-up areas. Okay, so the photos that I used to show the 3 different categories of rock type, they were all from international examples. They were from France, from the US, and from Sweden. So I think I've made the point really that UK is not alone in facing the challenge of how to permanently dispose of its nuclear waste. So I've talked about Finland, Sweden, France, USA, Germany, also facing the challenge. Switzerland has just this year announced the site at which they will construct their GDF. It's fairly near to Zurich in North Switzerland, not that far from the German border. And like France, their facility will be constructed in, again, Jurassic claystones, so very fine grained claystones, about 800 meters beneath the surface. So it's really useful for the UK to be able to collaborate with these other countries, and there are more countries that I've not shown here, in particular Canada, I could have talked about. Really useful for the UK because this is one of those industries where there isn't really a competitive advantage. All the different countries that are thinking about how they're going to construct a GDF and where they're going to construct it and the kinds of rocks they're going to put it in are very interested in sharing their ideas, sharing their technology, and making certain that the global community really comes up with the best solution for solving this really difficult problem. Having said that, different countries, as you can imagine, have different policies. So UK policy, for example, is very much built on what's called community consent. So you might have a question for me at the end of this talk that says, well, Jonathan, where are you going to put it? And the answer to that question is, I don't know, and we don't know, because it's not actually my decision. What we're involved in at the moment is talking to different communities about the benefits of their hosting a GDF in their area. So you might say, well, why on earth would anyone have nuclear waste disposed of in the area where they live? And the answer to that is that This program will last about 160 years, so take about 160 years to construct your GDF, to fill it, to backfill it and seal it and decommission it. It will involve up to £50 billion of investment in jobs, in roads and railways, possibly in a seaport if it's near the coast, possibly in sea defences. So you can see that communities have the potential to be completely transformed by that scale of investment over a period of more than 100 years. But the point of this slide is just to remind you, other countries are facing the same challenge as the UK. Okay, just a few words about how we will find out what the geology is like hundreds of meters below the surface. And well, the answer to that is we will eventually use deep investigation boreholes, very much like the way in which the oil and gas industry drills boreholes in order to explore for oil and gas. And we'll also use geophysical data. So you might have heard of seismic data, which is a method for bouncing sound waves off layers of rock up to several kilometers beneath the surface and reconstructing a picture of what that rock looks like. So when I say we, Nuclear Waste Services, my company, just last summer has completed the first seismic survey, so acquiring that geophysical data that I showed in the last slide, off the southwest part of Cumbria, so just sort of southwest of the Lake District National Park in the Irish Sea. This was the ship that carried out the seismic survey, belongs to a company called Shearwater, and this was cruising up and down sort of between England and the Isle of Man for a period of about 4 weeks, acquiring about 250 kilometers squared of seismic data. So that's pretty exciting for the UK because this is the first specific deep geological data that's been acquired for the in order to understand the potential of the geology for deep geological disposal of nuclear waste in more than 30 years. So we are making pretty good progress. So I just wanted to spend the last part of this talk thinking about isolation. So in describing the three main types of rock in which a GDF could be constructed, I talked about fluid flow, didn't I? I talked about the need to demonstrate that fluids move only very slowly through those sorts of rocks. And the reason that's important is because we need to demonstrate that the rocks and the engineered systems can contain or seal in the nuclear waste for a very long period. But the reason for building the GDF so deep underground is we need to isolate it from processes that are occurring at the surface. Now, as you can imagine, Nuclear Waste Services isn't able to design a GDF and then just go ahead and construct it. We need to demonstrate to independent regulators that our designs are going to do what we need them to do, and that the nuclear waste will remain disposed of, sealed in deep underground for up to 1 million years. That's the length of the timescale over which we will need to demonstrate safety. Now, 1 million years is an almost unimaginable amount of time, isn't it, in which to have to demonstrate that a facility like this is going to be safe. And as soon as you start thinking on the scale of hundreds of thousands or 1 million years, there are all sorts of processes happening at the surface which seem bizarre to us on our historical timescale, but which we need to take into account. So let me just name 3 of those. The first is sea level change. So the map on the right shows you that as little as 6,000 or 7,000 years ago, so much water was locked up in the ice caps that sea level was considerably lower than it is today, such that you could have walked to France, you could have walked to the Netherlands and Germany and Denmark, and you could almost have walked across to Norway. So the English Channel only actually finally separated France from southeast England about 5,500 years ago. The photo on the left there is of a little village in northwest Wales, in Gwynedd, called Fairbourne, which is significant because it's the first settlement, it's the first place in the UK which is going to be given up to sea level rise. So the local council have announced that from 2050 they will stop maintaining the sea defences. And that means over a period of a few years, the sea will come in, and that scene that you can see there, the village of Fairbourne, will eventually become submerged beneath the waves. So sea level rise is something that we're beginning to see on our sort of human timescale because of climate change and all the things that we know about. But over a period of thousands, tens of thousands, hundreds of thousands of years, it could be really significant. Now, why is this important for a GDF? Once the nuclear waste has been placed underground and the GDF has been sealed off, sea level rise is more or less irrelevant because that sea level rise doesn't affect rocks hundreds of meters below the surface. But the reason sea level change is relevant is during the 100-year, 160-year period when the GDF is in operation, we'll need to make certain that it's protected from any storm surges, any inundation from the sea, because water doesn't mix well with nuclear materials, as you may know. So sea level change is one of the processes that we need to take account of on that very long, up to 1 million years timescale. The next one I want to talk about is glaciations, not unrelated to sea level rise. So the photos that you see here are taken from a pretty much identical viewpoint. They're of a glacier in Iceland, and the photos are taken 20 years apart. So I've given the name of the website there where you can see something like 160 of these different examples of glaciers in Iceland, showing how climate change is causing the glaciers to retreat. The reason I've showed these photos is that in the photo in the bottom right there, you can see that the retreat of the glacier has exposed some huge cliffs. Hopefully you can just see that. My pointer isn't working, so I can't actually, let me just try once more. No, it's not working. I can't actually use my pointer to point out, but you can see just at the end of the glacier in the photo in the bottom right, there are some huge cliffs exposed there. And it's this kind of erosion that is associated with glaciers that means that the GDF needs to be at least 200 meters beneath the surface, because we need to take account of deep erosion that could occur due to future glaciations. There are a whole range of other processes associated with glaciations that we need to take account of in designing the GDF. Let me just name one other. Two others, in fact. One of them is permafrost, so frozen ground that can extend up to 0.5 kilometer below the surface and completely changes the pattern of water movement in the rocks deep underground. And then a second process worth highlighting is that glaciations are often associated with a huge flood underground of water that's very rich in oxygen, and that can accelerate the corrosion of the metal canisters, which then effectively rust. They generate gas, and that gas I've spoken about already can be one of the challenges that we face, in that gas is one of the ways in which radio or nuclear materials could migrate to the surface. So understanding processes associated with glaciations, really important for us once you start thinking on that million-year timescale. And then lastly, and you remember I'm talking here about processes at the surface from which the nuclear materials need to be protected. This is basically the reason why we're putting these materials deep underground. Earthquakes. The UK is not particularly prone to earthquakes. We're not on a big plate margin. You might have seen in the news 3 days ago, there was a sizable earthquake that affected Indonesia, but Indonesia sits on a major tectonic plate margin. So does Iceland, so does Greece and Italy and Turkey, but the UK sits pretty much in the middle of a plate, long way from plate margins. Doesn't mean to say that we don't have earthquakes. Your parents might remember an earthquake that affected the Birmingham, West Midlands area in the 1990s. Some nice old 19th century photos here showing earthquake damage in Essex in southeast England. And earthquakes, of course, are associated with shaking. Well, that shaking is far less severe deep underground, and they're also associated with cracks forming in the rocks deep below the surface. So again, we need to design the GDF and to be able to demonstrate that we've designed it to take account of shaking and cracking associated with earthquakes. So at that, I'm going to hand back to Abby. Thanks very much for your attention. And I just urge you, if you've got any questions, they might be on geology or science or anything else, please ask. There's no such thing as a daft question. So Abby, thanks very much.
So we'll get started with the Q&A session. So if you have any questions, please put them in the chat, type them into the chat, and I'll read them off one by one. So we already have a question in the chat from Arnav. So could you please explain in detail why it is important that the pH level of the cement mixed with the nuclear waste is high?
Yes. So lots of experimental evidence that shows that radionuclides, so radioactive materials in the form of colloids, are a lot less mobile in high pH materials. So all of the cements and grouts that we use as part of what's called the engineered barrier system. So there's a whole range before. I mean, I've spoken quite a lot here about the geology and the different rock types and rock characteristics in which a GDF could be constructed. But those canisters and packages that I showed in one of my photos are encased in what we call an engineered barrier. So this is a whole range of different sort of plugs and seals and backfills. And one of the common characteristics of those engineered barriers is high pH, high alkalinity, because it minimizes the mobility of radionuclides.
Okay, thank you. I have a few questions from myself. So with developing countries, and how would they invest into deep geological disposal? So are there any alternative solutions that they could use instead?
There are. So I don't think I said it, I sort of implied it, but the UK, France, and the US have by far the largest nuclear waste stockpiles in the world. But you're absolutely right. There are many other countries that have got 1, 2 nuclear reactors. So they've got a much smaller quantity of spent fuel to dispose of. So I think what you're getting at is, do those countries need to go to all the expense of constructing this fairly sizable mine in order to dispose of such a small volume? And the answer is there are other solutions. I mean, other than the GDF solution that I've talked about for small volumes of waste. And one of them that I'll highlight is called deep borehole disposal. So basically drilling deep boreholes, so at least 4 kilometers deep, vertical boreholes at least 4 kilometers deep, and stacking within those boreholes canisters containing nuclear materials. So very special ways in which they're stacked. But the point is about deep boreholes. Once you go below about 3 kilometers, 2.5, 3 kilometers in the earth, the pressures are such that the fluids in any sort of rock move only very slowly, and therefore deep borehole disposal is has a high potential for countries that have a small volume of waste For Britain, it wouldn't work because we've got such a large stockpile of waste that we'd need to drill dozens, scores, hundreds of boreholes, and it would be prohibitively expensive.
How wide would those holes be?
So you might have seen on one of my slides, the slide that showed the boreholes and the seismic. I said that standard oil and gas industry borehole technology, by the time you get down to the sort of depth at which we might construct a GDF, the diameter of the borehole is about 200 millimeters, about 20 centimeters. So that would be no good for deep borehole disposal. So the companies that are pursuing this idea of deep borehole disposal are developing technologies which would mean that you could drill boreholes at least 1 meter diameter, much less than that, and you wouldn't be able to get a decent sized package into the borehole.
Yeah.
So it would, I mean, it would be fairly routine in terms of the way in which a borehole would be drilled, but it would require a whole load of new hardware that meant you could get down to the sorts of depths needed deep below the surface and still have a borehole that was wide enough, about 1 meter as a rule of thumb. So there are some challenges there. That's not technology that's ready to go, sort of on the shelf.
There's been another question in the chat. Could you expand more on the impacts, both benefits and costs, of building GDF in communities? And to what extent do communities have a final say on their implementation?
Well, I'll take the last bit first. And to what extent do communities have the final say? Completely. And I mean that most sincerely. I don't necessarily recommend it, but if you read UK government policy on nuclear waste disposal, it is very clear from page 1 that this is a community consent-based process. If that wasn't the case, I mean, in your introduction, you mentioned I've been in this industry for 6 years, having come from oil and gas, but the UK has been pursuing or trying to find a location for a GDF for more than 30 years. Now, the reason for that is because the community consent has been very difficult to obtain, and it's a long story, and I haven't got anything like enough time to go into it now. But basically, our predecessor company, which was called UK Nirex, made a mess, I think I can be fairly frank about that, of how it engaged with local communities. And I think we're in such a better place now. I showed the seismic boat that has acquired new geophysical data in the Irish Sea. That all happened because the local community in the southwest part of Cumbria, an area called Copeland, gave permission for that survey to go ahead. And the questioner asked, will the community have the final say? They will have the final say through what's called a test of public support, which is a sort of referendum. And that enables the community to say thanks, but no thanks. Even if we'd invested £500 million in investigations and boreholes and seismic, the community is in charge all the way. So this is not a case of me getting out the big geological map and getting a pin and saying these are the best places. It's all based on working with communities and helping them to understand, well, two things really. One is what I've talked about today. What is nuclear waste? What's the solution we have to dispose of it? In other words, is it going to be dangerous for them? But then the flip side of the coin is that £50 billion investment over more than 100 years in roads, railways, ports, sea defences. A lot of communities are very interested in sea defences. And then the last thing I'll just mention, I mean, I've dwelt on this question for quite a long time because I think it's such an important question, is that some communities are concerned about the drop in house prices as soon as it's announced that Nuclear Waste Services is considering building a GDF in their area. So we are part of, we've got a large team within my company that deals with what's called property value protection. That in other words, if we're able to demonstrate that a house has dropped in price as a result of NWS, my company, carrying out investigations will make up the difference in price. So really, really important that we can keep communities on side. If we make a mess of that, we're back at square one.
Yeah. Are there any sorts of companies or government organizations that are planning to create a undersea GDF? Are there any in like the next couple of years or next decade?
Well, yes, we are. So, you know, I've talked at length there about community consent, and that community consent takes place through what's called a community partnership. And my company, NWS, presently is engaged with 4 community partnerships, 3 in northwest England and 1 in Lincolnshire on the east coast of England. And all of those 4 community partnerships are interested in, you remember the cartoon that I had, they're interested in a GDF in which the surface facilities are at the coast, but the waste disposal areas are beneath the seabed. So on the west coast of England under the Irish Sea, on the east coast of England under the North Sea. So yes, at the moment, all the 4 options that we are pursuing, and this is all public knowledge, by the way, you can go on our website and see exactly who we're engaging with, but all the 4 options we're considering are to have the waste disposal areas beneath the seabed. And that's why the geophysical data, that big boat the big ship that I showed a few slides ago, you know, that it's a ship rather than a land-based geophysical survey, because we're trying to understand the geology beneath the seabed, beneath the Irish Sea.
Yeah. With some of the surface nuclear waste facilities, if they were to be, say, attacked, what would the effects of those be? So, for example, in Ukraine, or Russia's been trying to attack some of the like old nuclear power plants. So, what would the effects of that be if they were to be attacked?
Did you say attacked?
Yeah.
Yeah, sure. Yeah, it's I mean it's going on right now as we speak, isn't it? You know, Chernobyl was on the news a few months ago, but Europe's largest nuclear reactor in southeast Ukraine, a place called Zaporizhia, is presently occupied by the invading Russian forces. So let me just take a sip of water. I mean, in many ways, Abby, your question highlights why we need to accelerate this program and put this hazardous material underground out of harm's way. You know, I showed the map that showed about 25 sites around the country where nuclear material is presently stored. And, you know, storage implies that temporary, doesn't it? But, you know, this program is about permanent disposal deep underground out of harm's way. And, you know, we can all imagine what I mean by harm's way. It might be terrorism, it might be an airline accident, it might be, you know, the kind of scenario you're talking about, civil war. It's unlikely in the UK, isn't it? But, you know, almost nothing's impossible, especially when you think on very long timescales. So I think that's exactly the reason why we need to, you know, forge ahead with this. And then the other one is the cost. You know, at £3 billion a year, that cost will be inherited by you, your young person's generation, the next generation following you, the one after that, forever, until we actually come up with a permanent disposal solution. That £3 billion a year, in order to ensure the security, will continue forever.
Yeah. There's been another question in the chat. Do you think we should be switching to renewable energy for our electricity and moving away from non-renewable energies?
I definitely do. Yeah. And you know, I think the UK generates more wind power in terms of megawatt hours than any other country in the world. We might have been overtaken by another country, but we're certainly top 2, top 3. We might be top 1. So I think we're doing well with renewables. Potentially, the UK is the Saudi Arabia of tidal energy. What I mean by that is we could be easily the world leader for power generated from tidal energy if we could, engineer a solution to harnessing the power of the tides. So I do, the reason why. So I showed the building site for Hinkley Point C in Somerset, and you might have heard on the news over the last few months that another reactor has got the go-ahead from the government in Suffolk. It's called Sizewell C, sort of northeast of London. And the reason why these tremendously expensive projects are getting government funding is, it's the old point that you probably heard many times. What do we do when the sun doesn't shine and when the wind stops blowing? We need to wean ourselves off hydrocarbons, oil and gas. We're doing a good job of putting in place as much renewables as we can, but Britain being Britain, sometimes you can't rely on renewables for sustained power generation, and that's where nuclear cuts in. But yeah, I mean, the short answer is yes, I do.
Okay. Okay. Thank you. I think we'll finish there unless anyone's got any other questions. Okay. So thank you very much for giving the talk today. Yeah. You have any?
That was really interesting. Thank you.
It's a pleasure.
Okay. Thank you, everyone. Bye-bye.
Thanks very much, Abby, and well done organising.
Thank you.